Hello everyone, welcome to problem set number 3 examples. Now doing limits and derivatives. So derivatives, one of the most important ideas in calculus. Limits are how you get there. So use the definition of the derivative, double underlined. I'm going to change the problem. I'm going to make it x squared. So using the definition means take the limit as x approaches whatever number is being talked about. That's a 2. And then on the bottom goes x minus that number. On the top goes the function itself, x squared, minus when you substitute a 2 into this function. And when you substitute a 2, 2 squared is going to be 4. Yes, you're right. It's time to factor. That is a good suggestion. So factor this x squared minus 4. And that's the difference of squares, so it's going to be x minus 2 times x plus 2. And limits, after you do some algebra, we'll usually have this where it simplifies very nicely and it just leaves x plus 2. And since I've done the cancellation, I can go ahead and plug the 2 in. So that's going to be 2 plus 2. And that I can even do without a calculator. That is 4. So the answer is 4. So I'm done with this one, but I just want to show you, you could also use the power rule. With this one, it did say use the definition, so literally I needed to do that. But now I can check my answer by using the power rule. The derivative of x squared is 2x. Then plug in a 2. So it's going to be 2 times 2, which is 4. That is one of the wonderful things about math, that you can do something in 2 completely different ways, and yet you still get the same answer. Okay, what's next? I also wanted to do one like this. So find the equation of the tangent line. So we'll need to take the derivative and then plug in 4, and then that'll give us the slope. Of course, I changed it a little bit. So this is still going to use the product rule, and then we're going to plug in 0. So for the derivative, just as a reminder, the product rule goes, if you have a product, a times b, and you're supposed to take the derivative, then take the derivative of a and leave b alone, plus, now leave a alone and take the derivative of b. So this is the a and this is the b. So the derivative equals, so take the derivative of the square root, and that's one of those that we use so often, I just memorize it. The derivative of the square root is 1 over 2 times that square root. So we've done this part. Now leave the b function alone, plus, now just copy down the a function. And then, do you know what the derivative of e to the x is? Yes, you're right. It's e to the x. It's actually the only function that does that. The derivative of the function is itself. Now the next thing to do is plug in x equals 0. So f prime at 0 will be 1 over 2 times. This is just going to be 0 plus 1, so that means it's the square root of 1, and then e to the 0. This will be 0 plus 1, so that's just the square root of 1, and e to the 0. And e to the 0 is equal to 1, so this is 1/2 times 1. 1/2 times 1 is just 1/2. Plus, this would be a 1 times 1. So that means that it's 1.5, which I'm going to write as 3 divided by 2, 3/2. Now the derivative gives you the slope of the tangent line. We also need the point that it goes through. So x is equal to 0, but I don't know what y equals. Well, I just need to take 0 and put it back into the original function. So this would be 0 plus 1, so that's just 1. And then if I plug in 0 right here, e to the 0 is 1. So this is 1 and this is 1, which means that the y value is 1. All right, now just use the point slope formula. So y minus the y value of 1 equals the slope times x minus the x value of 0. So that means that the right side is just 3/2 times x. And to finish it, all I need to do is add 1 to both sides. So if you add 1 to both sides, this is the equation of the tangent line. Now, before you leave to go get a snack, let's graph it and see if I got it right. So I first need to turn it on. Oh, did you see that? Look, if you look in the screen, you could see me. Where am I? Oh, right up the nose. No, never mind. Sorry. So let's see, y equals, the original function was the square root of x plus 1. And then move to the right to get, the contrast still isn't that great. Let me try again. Okay. And then times the e function, e to the x. And then zoom standard. And this is what the graph looks like. Now, for one thing, I could check and see if I got the derivative right. By the way, did you see that little yellow circle? So when that little yellow circle is going, that means it's still thinking about how to make the graph, and it won't let you do anything until that circle is done. So now that it's done, I can see if I got the derivative right, because I can go to second, calculate, and number 6 is the derivative. And then I just need to tell it x is 0. And right there, it says that the derivative equals a 1.5, and I got 1.5 or 3/2, so 1.5, that's the same thing. Good, got that right. I now need to check and see, is my equation right? So for my equation, so leave the original function, and now graph 3 divided by 2x plus 1, and see if that looks like a tangent line when x is 0 and y is 1. And that definitely looks like a tangent line. If I would have made some small algebra mistake, let's say I accidentally said, oh, the answer is a -1. And then you look at that, this red line, it's not even touching the graph. It's supposed to touch the graph right there at 0, 1. Then I realized, oh, wait a second. I meant to say this is a +1. And that looks like a tangent line. Then I just want to zoom in on that point to make sure that it looks correct. So zoom in on that point, hit enter, and then you'll see that the red line, especially if you're close to that point, so if you zoom in really close there, which I could do, zoom in really close to 0, 1, and then you'll see that at least when you're close to this point, the red and the blue graphs are basically the same. So within this region, right about that region, they're pretty much the same. And at 0, 1, they are the same. Okay, so by now I'm thoroughly convinced that I got that one right. Is there anything else we're going to do? Oh, I need to adjust the contrast, do the hand trick. And looking at page 2, find the derivative, set it equal to 0, and then solve for x. So for this one, you'll need to use the quotient rule. Seems like it's a little too bright. So for this one, you need to use the quotient rule. And for this one, the product rule. I'm going to do one like this. So I changed it just slightly, but it would go like this. First of all, do the product rule. So the derivative is going to equal, so for this one, take the derivative. That means use the power rule. So 7x plus 5 is now raised to the 6th. And now leave x minus 9 to the 12th alone. So we're halfway through the product rule. Now leave the x plus 5 term alone. X plus 5 is to the 7th. And now take the derivative of this one. So that means it's going to be 12 times x minus 9 to the 11th. Then set it equal to 0 and solve for x. Well, if you were to multiply this out, this is 2 terms to the 6th, and this is 2 terms to the 12th. That means it's 2 terms to the 18th. 2 terms to the 18th is, oh, sorry, you can't see it, but it's 262,000 terms. So this has over 250,000 terms, and this would also have a quarter. So that's like 500,000 terms. There must be an easier way. Yes, and it's called factoring. So this has x plus 5, and this has x plus 5. That means you could factor out x plus 5. When this has 6 of them and this has 7 of them, you can factor out the smaller number. So I can actually factor out x plus 5 to the 6th. X plus 5 is to the 6th. Now this has x minus 9, and this has x minus 9. And 11 is smaller, so I could factor out 11 of them. And this algebra would save me about a week's worth of multiplying out 500,000 terms. All right, now what's left? So going back over here, this is gone completely because I factored that out. And I factored out 11 of these, so one of these remains. So there's an x minus 9, and there's also a 7. So there's 7 times x minus 9. And then plus, so that's just this plus sign, bring it down. There would be the 12 left. And these x minus 9s all got factored out. 6 of these got factored out, so there's one more that has x plus 5. And then I could just, well, for now, recopy this and recopy this. And then, let's see, how many x's? So this is 7x, and this is 12x, and a 7 and a 12 is 19, so there's 19x. This is a negative 63, and this is a positive 60. So negative 63 plus positive 60 is a negative 3. All right, now we're practically done. Now you just set this factor equal to 0, and set this one equal to 0, and set this one equal to 0. When you set this one equal to 0 and move the 5 to the other side, it's going to be x equals negative 5. Right now there's probably somebody saying, hey, what about this 6th power? You can't just ignore that. Okay, if I show all of my work, it goes like this. Take x minus 5 to the 6th, and we're setting it equal to 0. Then take the 6th root of both sides, and the 6th root and the 6th power will cancel each other out. And the 6th root of 0 is 0, and so I get the same thing. X equals a negative 5. Likewise, over here, when you put this equal to 0 and move the 9 to the other side, it's going to become a positive 9. And finally, for this one, I would set it equal to 0, and then add 3 to both sides, becomes a positive 3, and then divide. So instead of dealing with 500,000 terms, we're done within just a couple of minutes. Thank you, algebra. Thanks for the help. And there was one more I wanted to do, and that is like number 6. So find the equation of the tangent line. So that means take the derivative and then plug in a pi. For this, you'll need to use the product rule. So I'm going to use sine squared. And look, I even reminded myself to use the product rule so that I'm doing basically the same type of work that you need to do on number 6. Well, sine squared, since it's squared, it literally means take sine of x times sine of x. All right, now I can take the derivative by using the product rule. So, you know what the derivative of sine is? You're right, it's cosine. So take the derivative of the first sine, but leave the second sine alone. Plus, the product rule says, leave the first sine alone and take the derivative of the second sine, which is cosine. So this is sine x cosine x, and this is also sine x cosine x. So that means we have two of them that are sine x cosine x. Or you could switch the order and say 2 cosine x sine x. It gives you the same thing. The next thing to do, plug in pi over 2. So y prime is 2 and then sine of pi over 2 and cosine of pi over 2. And you know what that equals? Yes, it equals 0. The reason I know that without a calculator is because if you look at the cosine graph, it looks like this from 0 to 2 pi. In the middle, that would be pi. And then right here, that's pi over 2. So that means that the cosine function at pi over 2, it equals 0. So this is going to be blah, 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 whatever, times 0 equals 0. Now, find the equation of the tangent line. So this is the slope. We also need the point. So we've got slope equals 0 at the point when x equals pi over 2, and I don't know what y equals. So I need to take a pi over 2 and plug it in here. Oh, you know what? I don't think I need a calculator for that either. You know what? Just for extra fun, I think I'll use the calculator. Of course, I have to adjust it. So I believe the answer is going to be 1. Okay, for one thing, make sure that it's in radians, and then go sine of pi divided by 2, and it has to be squared. It equals a 1. Okay, so the y value is a 1. So the y value is a 1. Now find the equation of the line. So y minus the y value of 1 equals, the slope is 0, and then x minus pi over 2. Which actually simplifies very nicely because this is just 0. So once you move the 1 over, since this is 0, it's just going to be y equals 1. All right, so that's it for problem set number 3. I'll see you back here for problem set number 4.